This lesson is for section 7.3. We're going to be taking a look at Pascal's triangle and using that to complete a binomial expansion. So that's our main objective. So first we have to talk about what a binomial expansion is, and then we'll talk about what Pascal's triangle actually is as well. So whenever I say a binomial expansion, that means we're just taking some binomial, a plus b, and raising it to a power. That's what it means to expand a binomial. So of course, a plus b to the 0 power, that's really easy for us to do. We just get 1. A plus b to the first power, same thing, pretty easy. And a plus b squared is also pretty easy for us because we can take our first term, square that, take our last term and square that, and our middle term is going to come from multiplying, finding the product here of a and b, and then doubling it, so we get 2ab. So those are quick for us to do. But as soon as we get to higher powers, then we have to do a little bit more work here, because to get a plus b cubed, I would take a plus b squared and then multiply it by another a plus b. That would result in this product here. If I wanted to find a plus b to the fourth, I would take that a plus b cubed and multiply that by another a plus b. So you can see how I'd have a lot of work to do here to multiply all of these out. So what we do is look for patterns in this binomial expansion, and then we can apply Pascal's triangle to it as well. So let's take a look at some of these patterns. Now I've summarized the patterns down below. So this is in the expansion of a plus b to the n, where n is any power. Now notice that there are always n plus 1 terms, meaning here it's raised to the 0 power. Then I get one term, exactly one more term than the power. So here I have 1 power of 1, here I have 2 terms. Here I have a power of 2, 3 total terms, and so on. So that means if I ask you to find a plus b to the 30th power, you know automatically that there should be 31 terms in that product. Also, the expansion begins with a to the n and ends with b to the n. So for example here, if I looked at a plus b squared, here I have a squared. It begins with the first term to that power, and it ends with our second term to that same power. Likewise, a plus b cubed, you have a cubed and b cubed, a to the fourth and b to the fourth. So it's very interesting. The sum of the exponents in each term is n. Okay, so the sum of the exponents is n. So here, the first term here, the sum of my exponents is 0, which matches here with n. In my a plus b to the first power, each of these terms here has a power of 1. So overall, this has to match that power here. In a plus b squared, you have a power of 2 here. The sum of these powers ends up being 2 as well. Here I have a power of 2 as well. So each term here, the power on your term ends up adding together to be n. Okay, so for a plus b cubed, here I have power of 3. Here I have 2 plus 1, which would give me 3. So there's an invisible 1 there. Then 1 plus 2 gives me 3, and so on. Okay. The next pattern here that we see, the exponents of a decrease by 1 from term to term. So here I have a to the first, then I have a to the 0 times b, so they decrease. So a to the 0 is just 1, which is why I'm just left with b. Here you can see numerically, here I have a power of 2, then a power of 1, and the last one would be a power of 0. A cubed, then a squared, then a to the first, then a to the 0. A to the fourth, a to the third, a squared, a to the first, a to the 0, and so on. You can also see that the b term increases by 1 from term to term. So here we have b to the 0, then b to the first. Then we have b to the 0, b to the first, b to the second, b to the 0, b to the first, b to the second, b to the third. So I know I'm kind of being repetitive, but it's very important that you see that the terms for the powers on a descend, and the terms here in the powers of b, they increase by 1. Now another few things to point out is that when n is even, so if we're raising it to an even power, the coefficients are symmetric about the middle term. So here's an even power. See how we have a coefficient of 1, 2, and then 1. They're symmetric about this term here, so they're the same on both sides. If we go to a power of 4, another even one, we have a coefficient 1, 4, 6, 4, 1. So it means that you see symmetry here about that very middle term here. When we look at an odd power, it's symmetric about the two middle terms. So for example, let's do one where it's easier to see. So for a plus b to the third power, we have a coefficient of 1, 3, 3, 1. So it's symmetric about these two terms here. For fifth power here, we have 1, 5, 10, 10, 5, 1. So it's symmetric about the two middle terms. So everything on the outsides here, kind of like a palindrome almost. So those are some very important patterns that you're going to use when trying to do your own binomial expansion. Okay, so the patterns that we saw in the expansion of a plus b to the n combined with something called Pascal's triangle, that's going to help us to do expansions like 3x minus, let's say, 4 to the 6th power. Okay, this would be very tedious for you to have to do, 3x minus 4 times 3x minus 4 times 3x minus 4 and so on, right? You're going to have to do so many different multiplying of terms, and it would get very crazy. So we use Pascal's triangle and our patterns that we saw in order to do this a lot quicker. Now it's not going to be a slow process, but it still is much quicker than having to do that longhand. So let's talk about what Pascal's triangle even is. Okay, so Pascal's triangle is actually an array of numbers. Okay, so it's just a pattern of numbers, and this guy who we give credit to, his name is Blaise Pascal, even though, and so he was in the 17th century, even though about 500 years earlier, a Chinese mathematician, Yang Hui, he actually drew something very similar. So in China, they give him credit for it because he kind of came up with it way beforehand. But basically, Pascal took a lot of time studying this. He came up with so many different patterns and a lot of mathematics. It's kind of cool. Pascal's triangle gives you lots of different patterns. We're just going to study, in relation to the binomial expansion, but if you ever wanted to look it up, it's kind of cool. Anyway, so basically this array of numbers represents the coefficients of the terms in the binomial expansion. So it's the coefficient of the terms in the binomial expansion of a plus b to the n. Okay, so I know that's a mouthful, but basically, remember when we took a plus b to the 0 power, we get 1. That corresponds here to that first row that you're seeing. When we take a plus b to the first power, we end up with a plus b. So you might think, how does that correspond to this? Well, that's the coefficients of a and b, 1 and 1. When you take a plus b to the second power, you get a squared plus 2ab plus b, or I'm sorry, b squared. So those are your coefficients here, 1, 2, 1, right there, 1, 2, 1. So on and so forth. I could continue to do that. It would take up a lot of room and time. But basically, if you trust me here, this just represents your expansion of a plus b to the n. Again, it's the coefficients of the terms. Okay, so that's going to help us now, because if we can memorize this triangle, we can come up with the coefficients very quickly, and then we can use these patterns here where we know that we have n plus 1 terms. Our expansion begins with a to the n and ends with b to the n, and our exponents of a decrease by 1, and our exponents of b increase by 1. So we'll do an example, but first I just want to make sure that we're comfortable with Pascal's triangle. Now to come up with Pascal's triangle, you can actually draw it pretty quickly. I'm going to do the 7th row here for you. So I call that row 0, row 1, row 2, row 3, row 4, row 5, row 6, and then row 7. To get row 7, we start with a 1. To get the next number, you're just going to add 1 and 6. So we get 7. Add 6 and 15 next, and you get 21. So you just basically add the two terms right after it. So you 15 and 20 gives you 35. 20 and 15, another 35. 15 and 6 gives me 21. 6 and 1 gives me 7, and you always end with 1. So I could get the 8th row and continue to do that, but let's start from scratch. So your row 0 starts with 1. The next row begins with 1 and ends with 1. The next row starts with 1. To get the next number, you add the 2 here. So 1 and 1 gives me 2, and then I end with another 1. I start the next row with 1. The next number comes from adding 1 and 2 together. I get 3. Add 2 and 1 together, I get 3. The last term is always a 1. So that's how you can quickly come up with Pascal's triangle. So again, I start with 1. I add 1 and 3, I get 4. Add 3 and 3, I get 6. Add 3 and 1, I get 4. The last number is always just a 1. So this is going to take practice. It's not that hard, but you might make some small mistakes here and there. But you can quickly see how you can get a lot of the rows just by adding. Okay? So how do we now use that when we're expanding? So here I've got expand the binomial using Pascal's triangle. So here I see it's to the 4th power. So off to the side here, the 4th row, and I know that I'm going to do these kind of quickly, but you should be able to do them quickly after you get just a couple times practice. That 4th row, remember that's 0, row 1, row 2, row 3, row 4, has coefficients 1, 4, 6, 4, 1 for all of your terms. So I'm going to draw blank after each of those numbers. So 1, and then another term, then a 4, then another term, then a 6, a term. Let me erase here. 4, a term, and then 1 and a term. So I'm just showing that I should have 5 total terms. So see how I have 1, 2, 3, 4, 5 terms. Again, that's the first pattern that we saw in the binomial expansion. I also have all the coefficients in front of the terms written here first, and then I have a blank just representing that each of those is going to be a term. Alright, now here comes the math part of it. Okay, so our first term here, that represents our a, right? So let's think of a as x, and negative 2 is going to represent our b. Now remember, in the binomial expansion, our first term is a to the same power that you're raising your expansion to, so it's a to the 4th, and if you want to write in b to the 0, you can do that, but you don't need to write that in, right? B to the 0 is 1. Now your next term, remember, your power decreases by 1, so that becomes a cubed, but your b power goes up by 1, so that becomes b to the 1st. For your next term, you should get a to the 2nd power, because again it decreases. B will increase. For your next term after that, so the 4th term here, I should have a to the 1st power and b to the 3rd power, and finally we'll end with a to the 0. Again, you don't need to write that in, but b to the 4th. So see how I start with a to the 4th and I end with b to the 4th. Okay, and everything in between goes down by 1, this one goes up by 1, down by another 1, up by another 1, and so on. So it's actually pretty easy as long as you just remember your pattern. Now I'm going to make the substitution in. Remember, we said x is a, so this becomes 1x to the 4th plus 4 times x to the 3rd. Now b, that value, is negative 2 to the 1st power. I don't need to write that first power in, but make sure you realize I always want you to put parentheses in, because I'll see a lot of students write that as 4x cubed minus 2. They think that turns into two different terms, but it's not. It's 4x cubed times negative 2. Okay, so we'll simplify this in a second, but so far these are the correct terms substituted in. Then I have 6 times, my a value is x, so x squared. My b value is negative 2, so I'm going to substitute negative 2 in there and square it. Then I have plus 4 times a, which is x, times my b value, which is negative 2 cubed, plus 1 times a to the 0. I don't need to write that one in at all, so I'm just going to skip now to the b, negative 2 to the 4th. Okay? Alright, now I just simplify, so I have x to the 4th minus, because negative 2 times 4 gives me negative 8x cubed. So this is where you got to be really careful. Again, if you don't have the parentheses there, it might look like it's 4x cubed minus 2. So you'll get 2 separate terms, and you're going to keep that positive instead of making that negative 8. So it's very, very important that you are paying attention to the signs and when you have to put parentheses around it. Okay, another point where you have to make sure you're being careful too is when you square this, you end up with a positive 4. So when I take positive 4 times 6, I get 24x squared. So really after that, it just becomes basically review of exponents. So when I simplify here, negative 2 to the 3rd power gives me negative 8. Negative 8 times 4 gives me negative 32x. And my last term here, negative 2 to the 4th power gives me a positive 16. So this is the final product that I would get if I were to take x minus 2 and have to multiply that out 4 times. Okay, this is that product here. So I think this is way faster, obviously, than trying to do all of that, by hand. So notice that your coefficients here don't remain 1, 4, 6, 4, 1. Your final answer doesn't necessarily have to contain the coefficients 1, 4, 6, 4, 1. But you should end up with 1, 2, 3, 4, 5 terms. And you can also see, remember how we talked about the sum of the terms? The exponents of the sum of the terms has to be equal to this here. So I have 4, and then 3 plus the 1 here gives me 4. 2 plus 2 gives me 4. 1 plus 3 gives me 4. And then that one here ends up 4. So it really should follow all the patterns that we've already discussed. And again, it's just a very quick way in order to do this problem so that you don't have to do that all by hand. Okay, so I know I went through that a little quickly, and now we're just going to get a couple more times to practice through this. It's really not too bad as long as you understand how Pascal's triangle works and how the pattern works. So let's start here with this binomial raised to the 3rd power. That means I need to get to row 3 in Pascal's triangle. Remember, row 0 starts with 1. Row 1 starts with 1 and ends with 1, so it has 2 terms in it. Row 2 starts with 1, and then to get the middle number, you're going to add 1 and 1, you get 2. It ends with 1, so we always start and end with 1. Then we need to get to row 3. So row 3 is what we're looking for. It's going to start with 1. We add 1 and 2 to get 3. We add 2 and 1 to get 3, and then we end with 1. So this is the row that we're looking for, and this will give us the coefficients of the terms of this binomial expansion. So let me erase everything else. So I'm going to write 1 and then a blank, because I'm going to fill that term here, plus 3 times a blank, plus 3 times another blank, and then plus 1 times another blank. Okay, so I've set it up. Now, I just want to double check here again that I have 4 terms. So I have 1, 2, 3, 4 terms. Remember, to find the number of terms, you just take 3 and you add 1 to it. That's going to tell you how many terms you should have in your final product. Okay, next I'm going to define my A term, which is 3x, and my B term, which is 2y. Whoops, not by. B equals 2y. Okay, so now from here, I just go ahead and I go through the pattern. Remember, you start with a to the third. Then you descend the power of a, so now it becomes a squared, and then times b. So we increase the power of b. Remember, this started with b to the 0 power, but we don't write that in. So now we have b to the first. Our next term will have a to the first, and then b to the second power, so we just keep increasing b. Finally, we'll have a to the 0 power and b cubed. After that, now we just make our substitutions. So I have 1 times 3x, so 1 times 3x, the whole quantity cubed. Make sure you're putting that in parentheses, because I'll see students who just write it as 3x cubed, and then they don't, get the right coefficient in front of this term. Okay, so the next term will be 3 times 3x squared times 2y, then plus 3 times 3x times 2y, the quantity squared, and finally plus 1 times 2y cubed. So I'm just dropping that 1 since I know that it's not going to change much there. Okay, so now I just go through and I simplify. In my first term here, I have 3x cubed, which is going to turn into 27 times that 1, so it stays 27x cubed. Then I have 3 squared, which gives me 9, so I'm going to just write all of this out. So I have 9x squared times 2y times the 3 out in front. So here it really doesn't make a difference what order you multiply them in, but sometimes it makes sense to actually do like doubling first and then multiplying by a 2-digit number perhaps. So try to find ways to be more efficient when you work through these. Here it's not too bad to just do 27 times 2 and double that one. But sometimes you're going to get numbers like 3 times 15 times 60 or something, and in which case you want to make sure that you're comfortable doing 2-digit times 3-digit numbers. Okay, so let's continue on here. Let's simplify. So I'm going to write the 27x cubed down. This will give me 54 times x squared y. The next term here I have 3 times 3x, so that'll give me 9x, and then times the 2y squared should give me 4y squared. So that term will become 36xy to the second. Final term here is going to be 2 cubed, so that's 8 times y cubed. So I have my final product here, which contains 4 terms. And if I look at the exponents here, these exponents add up to 3. So here the missing exponent is 1 and 1, but each term here, the exponents add up to 3. All right, last question here, number 3. This one's a little bit more difficult, and that's because we're going to the 5th power. So as you raise powers, the coefficients become a lot larger, and you're going to have more multiplication to do. But anyhow, let's get to the 5th row. So we start with row 0, which is 1. Row 1 is going to be 1 and 1. Row 2 is 1, 2, 1. Row 3 is 1, 3, 3, 1. Row 4 is 1, 4, 6, 4, 1. And row 5, the row we're looking for, is going to be 1, 5, 10, 10, 5, 1. So we've got our coefficients, so let's set it up. So we've got 1 times our terms plus 5 times our blank here, plus 10 times something, plus 10 times another blank, plus 5 times our blank, and plus 1 times our blank. Okay, so we've set it up. We have 6 terms, so we're good, since we know we are supposed to have 6 total terms in our final product. So I'm going to define a to be 2x and b to equal negative y. So it's very important here that you take that negative and you place it with the second term, so it's negative y. All right, now we're going to just do our substitutions. So we have a to the 5th power, then a to the 4th, b. So again, I just decreased the a term, increased the b term. Then a cubed, b squared, then a squared b cubed, then a to the first, b to the fourth, and finally b to the fifth. Okay, from here, let's make our substitutions. So we've got 2x raised to the fifth power. I'm going to ignore that 1 out in front. Plus 5 times 2x raised to the fourth power times a negative y. Make sure, again, I'm stressing this a lot, that you put this in parentheses, because I will see students write this as 5 times 2x to the fourth. They'll forget the parentheses there, so they'll get the wrong coefficient here. But then they'll write that as minus y. So they end up with 2 terms here, which adds another term, and so before they know it, they have like 8 or 9 terms, and they don't know where they made their mistake. So please always use parentheses when you make those substitutions. Okay, so then we have plus 10 times 2x to the third power times negative y to the second power plus 10 times 2x to the second power times negative y raised to the third power plus 5 times 2x raised to the, oh, so just to the first, so I don't even need to write that in. And then b to the fourth gives me negative y to the fourth. And then plus, let's scoot this over, negative y raised to the fifth power. Oh, that's an ugly 5. Okay, so now from here I just make simplify. So I've got 2x to the fifth power, which is going to give me 32x to the fifth, plus 5 times 2 to the fourth is 16 times x to the fourth times a negative y. So that negative y, I'm just going to attach the y here. I'm going to make that become a negative out in front. So that's very important here because it affects the overall term. So 5 times 16 here simplifies to 80. So we have 80x to the fourth y. Let's just clean that up a little bit. So 80x to the fourth y. Next term is going to become 10 times 2 cubed, so 10 times 8, x cubed. And then here, really important, it becomes a positive y squared. So you're taking the quantity negative y and squaring it, so you get a positive y squared. So overall, this term ends up being 80x cubed y squared. Okay. Alright, I'm going to switch colors here. Next term, 10 times 2 squared is 4x squared times this time here. Negative y cubed is equivalent to negative y cubed. So this negative will change the entire quantity here to a negative 40. Negative 40 x squared y cubed. Okay, then I have my second to last term here. Plus 5 times 2x times positive y to the fourth, which will simplify to 10x y to the fourth. And finally, that negative y to the fifth is going to become negative y to the fifth. So this should be a final product for the expansion of 2x minus y raised to the fifth power. Again, notice I have 1, 2, 3, 4, 5, 6 terms, and the sum of the exponents there add up to 5. Alright, that's the end of the lesson. Please make sure you try this next question here on your own. You're never going to know if you really truly understand how to do this unless you try this one on your own. So this one's going to be a little bit more complex. You're going to get a lot more multiplication here to do on your own. So if you need to cheat and use a calculator, that's fine. I know that some of this is tedious, but make sure that you can do 2-digit times 3-digit numbers here. Okay? All right, nice job. See you tomorrow.